square roots worked out to be nice numbers, and basically they were square roots of perfect squares, meaning that our answer ended up looking like just a whole number or maybe a fraction, but something relatively simple and straightforward. In a lot of other circumstances, though, in fact, in most circumstances, we won't end up with perfect squares. In fact, in a lot of circumstances, dealing with numbers in the real world, we don't even get whole numbers to begin with in our problem. And when we run into these sorts of instances, we are going to need to round the answer either as dictated by the significant digits that we have, or as will be the case with the homework as specified in the problem. Let's go ahead and look at an example where we have a bunch of decimal expressions in our equation to begin with. So just like we did at the beginning of the section, we can see that this thing's a quadratic equation because it has that x squared term. So we can go ahead and identify each of these values of a, b, and c here. So a works out to be 1.32, b is negative 5.61, and c is negative 0.98. Now, it doesn't hurt to go ahead and start by expressing this using our quadratic formula generally, and then we'll plug in the values as appropriate. So remember, we're taking this whole fraction of negative b plus or minus the square root of b squared minus 4ac, all divided by the quantity 2a. So as I'm plugging these values in, note that negative b are really the opposite of b. Since b is already a negative number, the opposite will become positive 5.61. And then we're going to take plus or minus the square root of, let me make sure I give myself plenty of space here, negative 5.61 squared minus 4 times a, which is 1.32, times c, which is negative 0.98. And then all of this is going to be divided by 2 times a. This is probably the most complicated formula we've had to deal with thus far. So it helps to chunk this thing up into smaller pieces when we're trying to do this calculation. So note first we've got 5.61, and then I've got this thing that's underneath the radical. I'm going to go ahead and combine both of these things in one step, just so I have one combined radical that I'm working with. Note that the first term, when we square it, we talked about the importance of parentheses before. Here we see it again. We're squaring that whole quantity, negative 5.61, which yields a positive value. Again, a negative number squared should always yield a positive value. If it doesn't, it's probably because we plugged it in our calculator incorrectly. In fact, when you're plugging this in your calculator, since you already know negative times negative is a positive, you might just choose to write 5.61 squared. What do we do with this thing? From that answer, we're going to subtract 4 times 1.32 times negative 0.98. And the answer is going to work out to be something that's not necessarily the nicest number. We're going to go ahead, though, and write that whole expression down. Better yet, we're going to use our calculator to preserve that answer and directly reference that answer when it comes to doing the computation. Because remember, we want to avoid rounding at intermediate steps because doing so can cause the resulting answer we get at the very end to end up being inaccurate. Now, we also have this thing all being divided by 2 times 1.32. So again, in order to simplify the expression that I'm having to plug into my calculator, I'm going to go ahead and multiply out those two values there together. We'll get 2.64 as our answer, or excuse me, as our denominator. Now remember that this solution is really shorthand for two different solutions, one where there's a positive square root, one where there's a negative square root. So let's go ahead and break this up and figure out what each of those values are, rounded to two decimals as specified. So the first one is what happens if I do plus this square root, and then divide by 264. The other one is what we get if we do minus that. Let me write out both of these numbers, and then we will compute each of these values here. And here's where we have to be super, super careful, again, especially when these numbers are complicated, not the sort of things that we can just simplify, right? There is no perfect, there's no value that just squares to be 36.6465. So the best we can do is simplify that numerator by doing 5.61 plus the square root of that 36.6465. Or we also could express that by doing the answer as well. So when I work out that numerator, I get 11.66. Again, we don't want to round it intermediate steps. We want to take this value and divide that whole thing by 2.64. When we divide that whole thing by 2.64, we get a value of, rounded to two decimal places, 4.42. If you want, you could plug this all into the calculator in one step, but if you do, you have to be very careful with parentheses. Note that the whole thing is being divided by 2.64. So if you choose to do it in one step, we're going to group together the numerator with parentheses symbols. There's kind of an implied set of parentheses whenever we're thinking about the numerator, but if we're using our calculator to do this all in one step, we actually need to be explicit with those parentheses, because our calculator doesn't know what we mean to write. All it knows is whatever we give it. So if we go ahead and do this, 5.61 plus the square root of this 36.6465. Anyone who's going to ever do any programming will know the importance of parentheses appropriately. Take a look at this expression that I just wrote here. I got a parentheses to indicate the numerator. That starts with that 5.61. But then I have another parentheses to indicate what I'm taking the square root of. That's something that my calculator does automatically. Yours might as well. So I need to close off that parentheses for the square root part, and then close off the parentheses for the numerator, and then, and only then, can I take that whole thing divided by 264. That yields the same answer. Now, if you're just thinking about this in a sort of like stream of consciousness kind of thing here, you might say, well, let's do 5.61 plus the square root of 36.6465, and then I have to divide by 2.64. If you do that, you'll get a different value. Because if we look carefully and think about order of operations, right? If I tell my calculator to do this, it's going to do the square root thing. It's going to divide that number by 2.64, and then it's going to add 5.61, right? Remember that division happens before addition in order of operations. So if you input it that way, you will get the wrong answer. So again, go to your comfort level. If you feel like putting in multiple steps into the calculator once you can, just be mindful that garbage in, garbage out, as they say, you need to make sure that you're plugging it in appropriately. So again, I'm going to go ahead for finding this one and just do it step by step, evaluate what that numerator is going to work out to be, 5.61 minus that square root of that value, and that number is going to be divided by 2.64 here. That number also has to be rounded to two decimal places as indicated in the problem, so that'll be negative 0.17. So putting it all together, my end solution here is negative 0.17 and positive 4.42. So just like before, we see we have two solutions to this. Now again, that's our kind of default with these quadratic equations, is we generally expect to see two solutions because of that plus or minus symbol that happens there. It really tells me for some problem I'm going to be adding, and then, or excuse me, for part of the solution I'm going to add that value, for the other part I'm going to subtract that value. However, there are some instances when we're trying to solve these ones, we'll actually end up seeing a negative value show up under the square root. Now we'll have more to say about negatives under the square root when we get to the very end of this course, but for the purposes of this section, when we're solving these quadratics and a negative shows up under the square root, we are going to observe that means there are no real solutions. The idea here being, as we kind of mentioned before, if you square a positive number, you get a positive. If you square a negative number, you also get positive. So there's no way to square numbers, at least not the numbers we're thinking about, real numbers, and get a negative value. So anytime you see the square root of a negative in one of these problems, it means you have no real solutions. Let's take a look at an example of how that might happen here. Imagine we have this equation x squared plus 2x plus 5 equals 0. It's hard to tell just by looking at it that we're going to get something weird out of it, but let's see, right, again, just to write down my quadratic equation one more time for good measure, b squared minus 4ac all over 2a. Note that a is 1, b is 2, and c is 5 in this equation. So we'll have negative 2 plus or minus the square root of b squared works out to be 4 minus 4 times 1 times 5 all over 2 times, oops, didn't need to write a, 2 times 1. So when we simplify that quantity that's under the square root, 4 minus 20 gives me negative 16. And just to kind of observe this, if you do this in your calculator, depending on your calculator, it might give you a particular sort of answer. But in this one, if I enter that, it's going to give me a domain error. We'll see that word domain show up in a future section. But basically, my calculator is saying, I'm not going to do that. I'm not going to take the square root of negative 16. That's not a thing I am programmed to do. So you're out of luck. I'm not going to take the square root for you. So in this circumstance here, when we see a negative under the radical, what this means is that there are no real solutions. Solutions are also sometimes called roots. So we could also say that there are no real roots. That's the phrasing that the homework system uses. All right, so that's just something to be prepared for. There might be a problem on the homework in which that happens, and just note that when you see that negative under the radical, you basically just stop. There's nothing more to do, no need to simplify it. Again, there is a meaning to it, but it's not the sort of meaning that we have any reference for yet. We'll have to save that until the very end of the course and see that in chapter 12. But as promised, let's go ahead and look at a couple of applications of this. One, the sort of thing that you will encounter in a physics class, for those of you who will take physics, and another, the sort of application in which you might encounter this in an electronics course. So let's start off with the physics example. We have a ball being thrown downward from the top of a tall building. And the distance it has traveled, you'll be able to derive this sort of thing when you get to physics. But we're just going to give us this formula that distance it has traveled is given by the equation s equals 16t squared plus 40t, where t is measured in seconds. Now what we want to know is how long will it take the ball to fall 100 feet? And we're going to round to the nearest tenth of a second. So if we read that carefully, we can observe that t is measured in seconds, and t is the thing that we want, whereas, oops, I forgot to mention this part. I'm going to fix this in the notes here. But s is measured in feet. So since s is measured in feet, that's actually the quantity that we are given to start with. So we have that this value falls 100 feet. So we want that s value to equal 100 at first. So in this equation, we will replace s with 100, and this equation is going to read 100 equals 16t squared plus 40t. In other words, there's some time at which this thing will have fallen 100 feet. So then, of course, the question is, how do we find that value of time? Well, now we've got a quadratic equation. We go ahead and employ our quadratic formula, right? We can observe that since there is a, well, here it's t squared instead of x squared, but we've kind of already seen in the previous section, it doesn't really matter what we call the variable. It's really just what operations are happening to the variable tell us how we need to go ahead and solve that thing. So first, if we're going to use the quadratic formula, because we can't use that square root principle because of the t term, then the first thing we need to do is get this thing to have a 0 on one side of the equation. There's a couple of ways to do that, but probably the easiest way is to just go ahead and subtract 100 from both sides. So then I'm going to write this right side as being on the left side instead, just reorienting the equation. 16t squared plus the 40t. We subtract the 100. If I subtract 100 from both sides, then I've got 0 left over on that right side. Well, solving this equation is exactly the same as the way we've solved equations before. The only thing I'm going to make a tiniest change, which is that instead of x equals, it's t equals. But again, the principle is exactly the same, but in a lot of applications, chances are you might not name your variable x. It might correspond to something like time. So here, let's go ahead and plug in those values. Observe that a is 16, b is 40, and c is negative 100. So if I plug in those values, well, actually, before I plug them in, let's just write down the formula one more time for funsies. Negative b plus or minus the square root of b squared minus 4ac all over 2a. All right. So we're going to have negative 40 plus or minus the square root of 40 squared minus 4 times 16 times negative 100. And that's all going to be divided by 2 times 16. Again, highly encourage you to go ahead and simplify your expressions before you try to evaluate these, just because these are kind of crunchy expressions. Let's simplify that radical part first. 40 squared, oops, let's clear the calculator. 40 squared minus 4 times 16 times a negative 100 means that my radical actually is kind of a nice number, 8,000. Unfortunately, square root of 8,000 isn't a nice number, so we are going to have to use our calculator for that part. But also observe that 2 times 16 could be simplified to be 32. Again, highly recommend that you simplify that just because if you're trying to input that in your calculator, note you have to divide both by 2 and by 16, so grouping those together first is a simpler way to do that. So we've got two solutions to this, right? And now these are going to be values of t, but it's the same idea. Negative 40 plus that square root of 8,000 over 32, and the other value of negative 40 minus the square root of 8,000 over 32. Now what does this work out to be? Okay, I'm going to go ahead and do this all in the calculator. Negative 40 plus the square root of 8,000. That's my numerator. My numerator here is 49.44, etc. Remember, you can just directly use that number without rounding, divide that value by 32, and it'll work out to be 1.545. Checking the directions it asks to round to the nearest tenth of a second. So note the digit that's to the right of that 5 is a 4. Since that is less than 5, this thing gets rounded down. Remember, we don't round the hundredths digit first and then round as a result, right? This thing is closer to 1.5 than it is to 1.6, and that's why we round it. So that's going to be, after 1.5 seconds, not a whole lot of time, this thing has fallen 100 feet. What about the other one? The other value is negative 40 minus the square root of 8,000, and then we're going to divide by 32. If we do that, we get a value of negative 4.0. What does that mean? Well, this is one of those things where we have to use context to be able to interpret this thing, right? If we're throwing a ball downward from the top of a tall building, right, it started here. You can think about it as a sort of experiment, if you will. You might get in trouble by throwing balls downward from the top of a tall building, but the experiment here starts at 0 seconds, right? You have to start gathering data at some point. Usually what we do is we say that point when we start gathering data is time t equals 0. It's basically specifying what we call a coordinate system for that, which means that anything that happens before the start sort of isn't really described by my experiments. In other words, this is a sort of nonsense answer. In this case, it doesn't make sense to say that the ball has fallen 100 feet 4 seconds before the experiment even began. That's weird. That's nonsense, right? So the algebra actually produced a value that in practice is actually a meaningless value. So that is to say, even though my equation produced two values, only one of them is actually meaningful. So that's the sort of thing that you will encounter a little bit on the homework, and you'll also encounter this again if you take physics. You'll see this exact sort of equation, and you'll see, in fact, more formulas built on these sort of quadratic principles here. One last one, I found this example here, that because of the way current is related both to voltage but also to power, which we'll explore a little bit more in other examples, you can do a little bit of finagling to show that the current in amps, which we measure with A, that letter A, in a circuit where you have a 100-watt light bulb connected in series with a 10-ohm resistor and an applied voltage of 120 volts, you end up getting this equation that relates all of those numbers. Again, don't need to worry about where that comes from for our purposes. We just want to take this equation that we have here and go ahead and solve it for I rounding to 3 significant digits. Now, we could take these values here and jump right into it, use the quadratic formula, right? We will need to use the quadratic formula because we do have this middle term, right? Again, it's the same exact thing as if it were 10x squared minus 120x plus 100 equals 0. It's just a different variable, so we'll just use the different variable instead of x. We could jump it right into that quadratic formula, but one thing you can do that will actually make your life just a little bit simpler is you might observe here that all of those numbers happen to be divisible by 10. In other words, you could divide 10 evenly into all of those numbers. So we're going to take a page from what we have done in a previous section and first actually do something to both sides of this equation. We're going to start by dividing both sides by 10. Because that'll just make the left-hand side a whole lot simpler. If we divide that whole thing by 10, 10 divided by 10, of course, is 1, so we'll just have I squared itself. 120 divided by 10 is 12, so we'll have minus 12i. 100 divided by 10 is 10. And then, of course, 0 divided by any number is just 0. So this equation is equivalent to that one, which is a little bit easier to use. Well, now we can go ahead and use that quadratic formula. Again, same exact formula. The only thing that's different is now it's going to be the letter I instead of the letter x. So, and I'll use these values from right here. Again, just to name them explicitly, A is 1, B is negative 12, and C is 10. So my expression here is going to be given by negative b, or opposite of b, works out to be positive 12, plus or minus the square root of negative 12 squared minus 4 times a, which is 1, times c, which is 10. All of this is going to be over 2 times a, or 2 times 1. Again, this will work out exactly the same if you started with this one up here. It's just the numbers are a little bit easier in this way. Well, just like we've done before, let's go ahead and simplify. I'm going to simplify the radical part. Negative 12 squared, of course, is the same as 12 squared, so I'm just going to write in 12 squared, minus 4 times 1 times 10, same thing as just 4 times 10. So 144 minus 40 gets me 104. So then 12 plus or minus the square root of 104 over 2. That really means two different solutions here. So one of those solutions is where we add the square root of 104 over 2, and the other one is where we will subtract, so 2 minus the square root of 104 over 2. Let's see if both of these solutions make sense. So we have 12 plus the square root of 104 divided by 2. So in this case, let's check what my directions asked for. They said round to 3 significant digits. So 3 significant digits in this context means the 10th digit, the 1st digit, and the 10th digit. Note that 10th digit will get rounded up. So then my answer here will be 11.1. Just given what we were told in the problem, this is measured in amps, which we abbreviate with the letter A. So that's 11.1 amperes or amps of current. The other possible way to get this to work is with this value. Let's see if that number makes sense. 12 minus the square root of 104. Take that value and divide it by 2. And actually, this number does make sense. If we want to round this thing to 3 significant digits, note that even though it's the same number of significant digits, the number ends up looking quite a bit different here. Note the first leading zero, any zero that is before all non-zero digits, counts as not significant. So significance starts with this digit, the 9. So the 10th digit, the 100th digit, and the 1000th digit are all going to be significant. That one is going to have to get rounded up because the one afterwards is larger than 5. So this thing, rounded to 3 significant digits, would be 0.901. So we do actually have algebraically two different solutions, 11.1 and 0.901. In practice, your electronics are going to be rated for some number of amperes, so you'll have to check whatever the electronics says. In fact, if you look at any adapters that you see, you will see all of this information written on it, how many amps of current do they draw, what's the voltage, etc., etc. So in practice, it would really just be one of these solutions that you would take, but algebraically, either one of them come out from that equation. All right, so that's all we have for this section. We have just a little bit more in this unit to talk about with ratio and proportion, which you will see in the next section. All right, have fun. On that side is subtract 3 from both sides. So then that equation is equivalent to this equation. Again, we added that 5x term, we subtracted the 3. Well, now at this point we can observe A, the number in front of x squared is 2, B, the number in front of x is 5, and C, my constant term is negative 3. Again, we could start off by writing that formula. I'm just going to jump right into the plugging in the values in this example. Negative b here will be the opposite of 5, and then we're going to take plus or minus the square root of 5 squared minus 4 times 2 times negative 3. And this is all going to be over 2 times 2. And taking my quadratic equation here, which we saw right above there, and simply replacing all of the numbers there with the values that we found. Again, this step, while not strictly speaking necessary, is really helpful because it makes the transition into using the formula a lot easier. When we just say, here's what A, B, and C are, then we can go ahead and plug all that stuff in. All right, what happens here? We'll get negative 5 plus or minus. Let's simplify the thing that's under the square root. 5 squared is 25. Note carefully here, I've got a negative 4 times a 2 times a negative 3. I'll show you this in the calculator, but you might be able to do this in your head. When I do that negative times the negative, observe I'll get a positive answer. I'll get positive 24 there. And all of that will be over 2 times 2. Although what I really should have written here is 2 times 2. Rather than just writing this 2 times 2, let's simplify it, right? 2 times 2 is, last I checked, 4. Well, let's go ahead and add up those numbers underneath that square root before we try to evaluate it. 25 plus 24 gets us 49. And again, 49 you might recognize is a perfect square. The number that squares to be 49 is 7. So my two solutions here are 5 plus or minus 7 over 4. Again, when it comes to solutions like this, we would much prefer to write them in as simplified a form as possible. So the two solutions we have here are -5 plus 7 over 4 and -5 minus 7 over 4. Well, if I add -5 with 7, I will get +2 over 4, which you might recognize. You can divide the top and bottom by 2. You'll get a value of a half there. So just like we've seen in previous equations, you might get a sort of fractional answer here. And then in this case, x equals, well, -5 minus 7, they're both negative, so you can add those and have the negative result, -12 over 4. That gets you a value of -3. So again, my solution is both of these values together, which we will separate with a comma. 1/2 and -3 are the two solutions. And if you feel like, you could go ahead and double check that you've actually done this correctly by plugging in both of those values. I will leave that to you as an exercise if you're curious. So we've seen a couple of examples here. We've got a couple more pages. We're going to see weirder stuff that happens, and then we're going to talk about what relevance this has. So what are some of the applications where we could encounter these kinds of equations?